Welcome to the FIK3505 Wireless Access Protocols course. This is a course intended for PhD students with a background in telecommunications. Presenting this course will be myself, Jens Sander. I'm a professor and director of the Radio Communication Systems Lab at the Communication Systems Department, the School of ICT, KTH, the Royal Institute of Technology in Stockholm, Sweden. The objectives of this course is to make the student understand and to be able to analyze wireless access systems. Efficient wireless access is important to share precious radio resources in, let's say, in cellular systems, in wireless local area networks, and for the Internet of Things. In these types of systems, thousands of smartphones, computers, millions of sensors and actuators need reliable wireless access to the Internet. After the completion of the course, the student should be able to understand the basic principles of multiple access protocols. The student should be able to define vital performance measures and to perform analysis of the performance of these systems, both by means of analytical solutions and by means of simulation. The course material used in this book is the book Multiple Access Protocols by Raphael Romm and Moshe Sidi. And in addition to that, we will use a number of selected journal articles. The prerequisites needed to follow this course is basically three parts. It's basic queuing theory. The student should be familiar with Markov chains and MMX queuing systems. We also require intermediate queuing theory as found in the book by Queuing Systems by Kleinrock, chapters 5 to 7. Polacek-Khinchin analysis and transform techniques for, in particular, Markovian deterministic queuing systems, MD1 systems. And the student should also be familiar with the basic busy idle period analysis technique in queuing systems. Also, some basic communication theory is required. The videos complement and highlight some of the main features of the material, but they do not replace the textbook. In the material there will also be quizzes. There could be multiple choice questions or there could be simple problems. When encountering these quizzes, please pause the video and try to make a serious attempt to answer the questions. Then restart the video and you get the answers. Here's an example. There are 4 statements and your task is to figure out which of them are correct. When you pause the video, you figure out the answers, and then you restart the video when you figured out the answers, and the answers will appear. Here, for instance, statements B and C are the correct ones. If you've missed any question, it may be a good time to review the previous part of the lecture. We now have a look at the rationale behind the wireless access protocols. Why are they needed and what are the different applications they can be used for? In recent years we have seen the network society evolve. One can say this has happened basically in 3 stages. The first stage is about moving from communications between humans to moving information around. The Internet information is about information anytime, anywhere. We need access to bank transactions, important documents, but also purely recreational stuff like movies and music entertainment. In the next step, we are now moving into the Internet of Things. It's not humans communicating, but the gadgets around us. We collect massive amounts of data about the environment, and this is designed to help us make informed decisions about the physical world. In the final stage, the Internet of Control, we move to also to control the physical world around us. It is clear that these different scenarios have very different technical requirements and require quite different technical solutions. Let's have a look how the Internet of Information is designed today. Today, the design is completely dominated by the cloud paradigm and IP, the Internet Protocol. Almost all applications today are designed where smartphones and computers are connecting to remote servers over high-speed, preferably wireless links, using the IP protocol. The Internet Protocol is a very simple interface, and that it's useful for all types of applications, and it has created an explosive growth since it works with all types of platforms. The drawback is that since it's very versatile, it's also quite inefficient, and you can say that we buy flexibility. It's useful for all things, but the required data volumes that need to be transmitted on these links is quite large. Specifically, you can say that the design now is so dominant it has replaced all types of other forms of communications. We do not connect smartphones to smartphone in a peer-to-peer connection if we want, for instance, to exchange a picture between two smartphones. Instead, both phones, they connect or using the IP protocol to the cloud or to remote service where the information is exchanged. This also means that specialized types of communications are no longer built. I mean, we don't build new systems only for one purpose, for example, TV or radio broadcasting. IP-based systems can, in fact, do it all. As my colleague Gerald McGuire usually says, IP is the answer. Now, what was the question? Let's look under the hood of the IP protocol. What is IP, or specifically TCP/IP? Well, a TCP/IP is a protocol that is designed to establish what is called a virtual circuit between two hosts. The hosts could be servers or laptops or smartphones. A virtual circuit looks to the connected host as if they have an exclusive connection through the internet. The TCP/IP protocol was originally designed to transfer files or web pages, and later it's also been used to connect streaming data as movies or music. The large file size is also reflected in the design of the protocol. As can be seen, the user data is encapsulated with a number of headers, and as we transfer large files, the user data sizes are large, could be thousands of bytes, and adding a few bytes of header doesn't really affect the efficiency of the protocol. But in other applications where we transmit only a few bytes of data, the overhead becomes significant and the protocols become quite inefficient. The focus here is on throughput. That means how many packets per second or how many bits per second can be transmitted on the average, rather than on the efficiency, how much of this transmitted data is actually user payload data, or neither is much focus on the delay or response time either. This illustrates the concepts of circuit switching or virtual circuit switching. In a TCP/IP connection, we set up a connection that connects two hosts. In the traditional old-fashioned way, the connections in telecommunication networks were physical connections, so-called circuit switch network, where for instance, user A was connected to user C, and user A transmitted its data in forms of packets, and connection between the two switching nodes were exclusively dedicated to the connection between A and C. And if user B wanted access the switching node signaling signal to user B that the connection was busy, and user B had to wait until user A and user C disconnected their connection. User B is said to be blocked. In a packet switch network, the lower part of the figure, user A and user B share the connection between the switching nodes. So user A and user C could connect a virtual circuit, each of them in parallel. And on the other hand, of course, the data rate experienced by user A and C on one hand, and user B and user D on the other hand, would depend on the amount of traffic that the other pair injected into the system. So the performance in the circuit switched network can be perfectly controlled by the network at the expense of users being blocked. In the packet switched in this virtual circuit network, the performance experienced by user A and user B will depend on the rate and the usage of the other users. If we move into the Internet of Things, or things that communicate, the requirements and applications may be very, very different. We may see applications from locating your dog, to controlling the heating in your apartment, to measuring the energy in your house, or even controlling the rush hour traffic in a big city. What we're dealing with here is systems for billions of devices. Sometimes they have very low power requirements, like the dog leash, which is battery powered, so we don't want to exchange the battery too many times. Some applications are very low cost. Tracking a parcel in the mail, for instance, is an example. If you attach a device there, that has to be a very low cost. It has to be in the range of a few cents. Some applications may have a very low delay requirement, some not. If you want to control a car in morning traffic, response times have to be very short. If you're interested in measuring the energy in your house, if the energy meter reading is delayed by a few seconds, that's not very critical. Summarizing some of the characteristics of the various types of applications. If you start with the infotainment traffic, what it's about, it's to transfer large files or streams of data. They have long duration compared to the typical setup times for virtual circuits. Delay requirements may not be that critical. If you set up and start a Netflix video, for instance, if it takes a few seconds to start the connection, that may be fully acceptable by the user. Of course, the system should work, but reliability is not that critical. If you have to once in a while have to restart your video from Netflix, that's probably annoying, but it's not really mission critical. And the performance measures that we'd like to consider is that we need a low residual bit error rate. We don't want the documents or the movies to be corrupted or show distortion. And the throughput, we want high quality video, for instance, so we need lots of bits per second that are transmitted to the user. In comparison, the characteristics of IoT data traffic are quite different. Here it's usually small messages or bursts of short duration, and these durations are very short compared to the typical setup time for a virtual circuit. And sometimes delay requirement is very critical, sometimes it's not. Controlling some remote device could require very short delay times, whereas sensor reporting, non-critical sensor reporting may be delayed without any problem. Sometimes the energy efficiency is very important. We don't want our devices to transmit 1 bit in excess of what is needed to conserve the battery life of the device. And reliability may or may not be critical. If it's a mission-critical device like controlling your car, the reliability requirements are very, very high. If it's reporting the energy in your energy meter in your home, if you miss a few readings, that's not very critical. Performance measures we need to consider are again, residual bit error rate. What is the error of the messages? The probability that a message that we actually receive is an error. The average delay. Often it's as fast as possible. Sometimes it's mission critical. Sometimes it's not. It's about energy consumption, and throughput may also be important at times. That's the average data rate. But normally these applications are more delay oriented rather than throughput oriented, as the amount of data transmitted is quite low. Having looked at the general characteristics of various types of data communication application, we now add the complexity of doing this in a wireless manner. In a wireless access systems, terminals, sensors, computers, they all need to compete for wireless resources connecting to a base station, as in this particular example. So what are the various problems related to doing all this wirelessly? There are two types of problems related to wireless networks. One has to do with the range or the coverage. In this example, we can see two mobile terminals connected to a base station. And as further and further we go away from the base station, the signal gets weaker and weaker, and at some point we can no longer reliably communicate with the base station. And what is critical is the signal to noise ratio, the energy to received energy to received noise energy ratio. And there are several factors that influence the signal to noise ratio, and it has to do with the transmit power of the various devices, PTX. It has to do with what types of antennas are used, what type of data rate is used, and B user here, and the distance R, how far away the mobile terminal is. And of course there are several constraints here. We cannot use too much transmit power, in particular if we have an energy constrained system. And in some cases the antennas, particularly the mobile devices, cannot be very large, so the antenna gain tends to be very low. And all this limits the range and the coverage of such a system. The other type of problem or limitation is very specific to wireless networks and has to do with that there's only one frequency spectrum that all the devices that want to communicate have to share. So in this particular example, we can see if Mobile 1 and Mobile 2 connect to base station A, they have to share the resources in base station A. It could be both the physical resources and transceivers and in the base station, or it could be the amount of spectrum that is available. But even if Mobile 2 connects to base station B, they still have to share the same spectrum, and if M1 and M2 transmit at the same time, they potentially could interfere with each other, lowering the data rate that is available to M1 and M2, or even cause destructive interference that even can completely ruin the communication if the interference is not managed in an appropriate way. This is probably the key feature that we will look at in depth in this course. Now let's have a look at the particulars of the course. There are mainly two types of problems that we will address in this course. First, we briefly have a look at the problem with the unreliable wireless channel. This is dealt with in communication theory, but we give a brief recap related to data transmission. How can we transmit over an unreliable channel that is prone to noise and interference? And that could also be time varying, where we have fading, we have the quality of the channel varies over time. The lion's share of the course, however, will be dealing with the resource management problem. How can we effectively use the spectrum? How can we effectively use the energy of the various devices involved? And the focus will be on situations that cannot be solved by virtual circuits, where the message duration is short compared to the setup or signaling time in a virtual circuit, and also where the demand is fluctuating rapidly. Mainly this is caused by there will be very, very many devices with low data rates each, so it's very difficult to predict the demand, how much data is going to be transmitted in the next time frame. The course will focus on performance analysis and analysis tools. We will describe some features of protocol implementation, and but there will be no really strong focus on this, and we will not consider the logical correctness of protocols. We will study the average performance of these protocols. First, we deal with the reliable transmission in wireless channels. Traditional communication theory tells us that if the channel deteriorates, if the number of errors in the channel increases, or the signal-to-noise ratio drops, we have to lower the transmission rate, either by using some different modulation scheme or by increasing the amount of redundancy in an error-correcting code. However, if we can relax the delay requirement, there's another way of achieving high performance, and that is by retransmitting erroneous messages. We focus on detecting errors and retransmitting errors. And it is possible to achieve very, very low residual bit error rates with rather low overhead in the number of checksum bits. However, the price we pay could be numerous retransmissions, so this is a way of trading low residual bit error rate against delay. And we will study some common ARQ, or automatic repeat request protocols, both in terms of how to retransmit, what strategies to use, and also how to design the error protection coding in the system. The goal is to achieve high efficiency. Efficiency is defined as the fraction of time that you spend for transmitting the actual data compared to the total time spent for transmitting the packets. Then we move to the resource allocation problem. Most throughout the course we will use a message-oriented model like the one in this graph. On the left-hand side we have a number of sources, users, applications that generate messages according to some random distribution, and they want to transmit their message over this wireless system to some receiver. In this particular example there's a single receiver on the right-hand side, but without loss of generality we can also think of models with separate different receivers on the right-hand side. The messages from the sources, they arrive at the transmitters T0 to Tm-1, And the problem we're faced with is to finding suitable strategies on how these transmitters should transmit their data over the wireless system. The wireless system has a limited capacity, and most of the time we will use a collision-oriented model, meaning that if too many transmitters at the same time transmit the data, the data may be lost. And they may receive information about this through the feedback link indicated as a dotted line with the Z, where the transmitters will be informed of the result of their different actions. Let us take a simple example to illustrate how this works. In this simple example, the wireless system is a time division multiple access channel, which means that there are a number of time slots here denoted 1 to 8 that can be allocated to the different transmitters in various ways. And there are a number of allocation strategies. The simplest one can think of is what we call fixed assignment. We assign slots to the different transmitters according to the average demand. And in the simplest case, if the traffic is the same on the average on all the sources S0 to Si-1, we simply allocate one slot each. So in this example, there are 8 slots, and if you have 8 transmitters, each transmitter gets 1 slot each, and the transmitter can only transmit its data in its slot. And if there are lots of packets being transmitted, this is usually quite efficient strategy because all slots will be full. However, if the traffic demand is very time varying or bursty, then it will very often be such that many transmitters have nothing to transmit, so many of the slots may be empty. And so it's of course wasteful if transmitter 1 has lots of packet to transmit and he sees that slots 2, 3 and 4, for instance, are empty, but he still has to wait for his turn to until next slot marked 1 turns up. Of course, ideally we would like to find out which transmitters have packets to transmit, and so that we can, based on the actual traffic conditions, we can find out what the actual demand is and assign slots accordingly. Of course, if the transmitters are wireless in a wireless systems, they cannot communicate directly, so this is difficult to find out. They have to use the wireless system itself to find out. We will also consider a hypothetical system, which we call perfect scheduling, where there were some magic wires connecting the different transmitters so that they can actually find out what is the situation, the traffic demand for the various from the various sources. That will be a hypothetical system where the demand is known, and this will be used to upper bound the performance of such a resource allocation scheme. So what will be the performance of these various allocation strategies? The graph here is a typical illustration of how we will evaluate the performance in this course. On the horizontal axis we have the traffic load. Here it's normalized to the capacity of the channel. 1 means that there will be exactly as many packets arriving totally to the system as the channel maximally can transfer to the receiver. On the vertical axis we have the delay. How long will it on the average take for a packet to arrive safely at the receiver? And here we can see the 3 different strategies. The curve marked FA is the fixed assignment, and we can see typical behavior that for very, very low traffic there will be still quite a high delay, and this has to do with that in the fixed assignment, even if there's no other traffic, we still have to wait until our slot turns up. In this case, this is a system with 20 slots, and so on the average in the fixed assignment, the user has to wait 10 slots until the slot marked with his number turns up. On the other hand, if the traffic gets very high, the fixed assignment asymptotically reaches the maximum capacity of the channel, although the delay will be quite high. The perfect scheduling, the red curve, has actually the same shape as the fixed assignment, but it's scaled to a much lower level. As you can see that in the perfect scheduling, if the channel is empty, there will always be the next slot will always be available to any user that has a packet. So the delay in the for very low traffic loads is very low, and it also has an asymptote lambda equal to 1. That when there's lots of traffic, all slots will be used, and the resource utilization will be very effective. The blue curve in the middle, dynamic assignment, shows similar behavior as the perfect scheduling. If we spend some resources to find out which transmitters have something to transmit, we get a very, very low delay when the system is lowly loaded. On the other hand, we spend resources to find out the actual demand. So the asymptote achieved by the dynamic assignment schemes is lower than 1, corresponding to the resources that we actually spend to determine the actual traffic situation. Some examples of dynamic assignment strategies that we are going to study in the course. There are mainly two categories. We have something called the random TDMA assignment strategies, where basically the different transmitters, they transmit the data without prior signaling, and they will use the information about successful received packets, or which you can call contention with other users, or collisions or lost packets, to determine what to do next. And this is very suitable for very short messages, and if you want a very short round trip and very short feedback delays. And if the traffic is rather moderate. If the traffic is low, then you can transmit, and there will be very, very few collisions and a little contention. When the traffic gets higher, and if also the messages that you have are long, you tend to use various types of reservation schemes. You spend some resources first to find out what is the amount of traffic that is need to be transmitted, and who's wants to transmit the information, and then you make reservations so that the actual data transmission is contention free. And this is, you can say, similar to the ideas in a virtual circuit setup. The final part of the course will deal with access management in multi-hop networks. In most of the course so far, we have been looked at the cellular paradigm, where lots of nodes access a single base station or a central receiver. In a multi-hop network, communication can go on between different entities across the area. If we use a TDMA type of allocation scheme, the problem is about how can we allocate different time slots to different receivers and transmitters. And we will look at two types of scheduling schemes, and one is the simplest one is, of course, the transmit schedule or node schedule, that every transmitter gets allocated a time slot, like in this case, where nodes A to E each get one time slot, and in this time slot they can transmit the messages whichever their intended receiver may be. The other scheme is what we call a link schedule. Instead of scheduling one time slot for every transmitter. We schedule 1 time slot for every link. And as you can see in the lower part here, some of the links can actually be used simultaneously. For instance, can A and B transmit at the same time as D can transmit to E. So we can make a more efficient use of the radio spectrum, allowing for frequency reuse.